Okay, so hi everybody, and welcome again to my lectures on Introduction to Quantum Theory and Technologies. So this will be the second part on the lecture on a review or a crash course, really, on the topic of linear algebra. So last week we started off by saying that, well, linear algebra is essentially a theory of vectors mixed with complex numbers. And where we got up to was talking about how to manipulate such vectors, and this is by the means of operators. So using operators, what we can do is we can change one vector into another vector, and this is basically like some kind of machine that takes one vector, you plug it into some operator, which I view as some kind of machine to change one vector into another, and this spits out a third vector like that. So generally we will work with such kind of linear operators like this. And what that basically means is that if you have a vector which is like a sum of two vectors, and if you operate on that sum of vectors, then it's actually the same thing as if you add the resultant of the two operated vectors individually. So that's just sort of a reminder of what we were doing last week. And so if you want to actually represent operators with matrices, then you can also represent them in a matrix form. And in this case, how it works is that the vectors are actually represented by, of course, as a kind of a row, like a column of numbers. This is in the component representation, and how you manipulate those vectors is by applying like a matrix to it, like this. So if you do a kind of a matrix multiplication, then you get a new vector, and this is basically how you operate on with in the component representation. Okay, so we talked a little bit about what the outer product was in comparison to the inner product. So an outer product actually gives you a, a matrix actually. So if you take these two vectors, sort of alpha and beta, and if you perform an outer product on it, because it's actually got the multiplication kind of first, the alpha is a vector, so it's like a column, and then beta is a row, so it's a row. So if you multiply this out, then you actually get a matrix like this. So an outer product actually takes two vectors and gives you a matrix. And this is in contrast to an inner product, which gives you a single number, a scalar number, when you take the inner product between two vectors. So these were some examples. So if you had two vectors, say E1 and E3, these are actually your basis vectors for, say, in a three-dimensional space. So E1 is the vector where the first component is 1, and E3 is the vector with the third component is 1. Then this makes a matrix where there's 1 and in one position here and 0 elsewhere. So this is actually why you can write any matrix by expanding it in terms of the matrix elements. These are your matrix elements, and multiplying by this outer product, you can make any vector. Okay, so we went through this example here, but I've already gone through that, so let's get on to what we're doing this week. So, okay, so matrices have, there's all different types of matrices that you can have, and there are some types of operations that you can perform on matrices that are some kind of elementary operations, and these are, some of them are very useful also in quantum mechanics. So I need to tell you a little bit about some of these kind of basic operations, right? So firstly, there's the so-called transpose operation. So the transpose is basically, the definition is that it interchanges the rows and columns of the matrix. So if you've got your matrix here and it's some kind of matrix here, then the transpose of this, which here actually I've taken this from Griffiths, I think. So the notation here, that he's got a tilde, which means the transpose. Some other types of notation that is often used is a little t. So if T is my original matrix here, here's our original matrix T, then so Griffiths uses this notation of putting a tilde on it as the transpose operation. But another kind of notation that people sometimes use is a little t, which is a bit confusing in this instance because the matrix itself is called T. This is maybe why he didn't use it, but a little t in the superscript is another kind of notation that you might use. In fact, this is, I think, the more common type of notation that is used. Okay, but regardless of what notation that you use, so what does the transpose do? Well, as you can see here, here is the original matrix T. So it's just a bunch of numbers, labeled by sort of the rows and columns. Then what it does is it puts that in that position there. So think of this, look at this diagonal, and basically you're going to flip it. Okay, so maybe I should do it this way. But basically along that axis that I'm drawing there, you are interchanging the rows and columns, so that T12 goes into that spot and that T21 goes into the spot where T12 was. And this is just the ones which are closest to this diagonal, but you can also you also need to interchange, say, all the elements which are on the off diagonal columns. So that element goes there, that element goes there. So T1n goes to Tn1, and Tn1 goes to T1n. And so that's how you end up with the transpose matrix. Okay, so that's the transpose, and that's just some kind of operation that you can define. But what's these types of matrices can give sort of special properties. And so, for example, you can define symmetric matrices where the transposed matrix is actually the same as the original matrix. This is called a symmetric matrix. So just a simple example of that, of a symmetric matrix might be something like 1, 2, 2, 3. Okay, so that's an example of a symmetric matrix, and if you interchange the rows and the columns, then you obviously get the same matrix because the 2 goes there, and then the 2 also goes here, and then they're both 2, so it's symmetric. An example of an anti-symmetric matrix would be something like this. So, for example, if I take, let's take an example where all the elements are, like, say, in this form. So, for example, if I take this case, then if I take the transpose of this, then what happens is that the 2 becomes a -2, and then that -2 becomes a 2, and the diagonal elements are all 0, so that actually is the minus of the original matrix there. So this would be an example of an antisymmetric matrix. In fact, I think it's impossible to have any matrix where the diagonal elements are non-zero because, of course, under the transpose, the diagonal elements don't actually go anywhere, and then it's impossible to have any number which is the negative of itself unless it's zero. So that's why this antisymmetric example needs to have diagonal components that are zero. Okay, anyway, these are just definitions. Another type of definition is the conjugate of a matrix, and okay, this time they use standard notation, so T star is that's the normal notation for it. And in this case, the conjugate of a matrix, as it sort of suggests, means you take the complex conjugate of every single element that exists in the matrix. Okay. So that's the conjugate of a matrix. Now, a bit like the transpose, there are kind of special cases where basically the conjugate actually does nothing. So these are, for example, the real matrices. So for example, if all the elements here were real numbers, then of course the conjugation does nothing, because remember, complex conjugate, what it does is if we've got any complex number a plus ib, then the complex conjugate of this, so if I take the star of this, then this becomes a minus ib, right? So a minus ib, so if the real part of the number is actually equal to 0, then, sorry, if the imaginary part of the number is equal to 0, then of course the complex conjugation does nothing, and so you get the same matrix. So if all these numbers are real, then it's a real matrix, and complex conjugation does nothing. On the other hand, if all these numbers are imaginary, so that means all the numbers are like, I something. So for example, here's an example of an imaginary matrix. So say I've got I and 2I, and then say minus I here, and then 3I here. This would be an example of a completely imaginary matrix, because if I take the complex conjugate of this, then all the numbers flip sign, and you get the negative of that matrix. Okay, so that's just some kind of terminology of the matrix. And we can actually combine both of these things, and this is actually the most important one for quantum mechanics. If you take the complex conjugate and you do the transpose, you can do that in any order actually, then say we start with the original matrix, which was T11, T12, T13, so forth, without the stars. So we do the complex conjugate and the transpose. So everything's got stars, and then the rows and columns are interchanged. Then this is the so-called Hermitian conjugate. Okay, and the notation of this is given by the dagger. So if you've got a dagger on the sort of the top right-hand corner of the matrix, then this means Hermitian conjugate. Basically means transpose and complex conjugation. Okay. Again, so there are special matrices where the complex conjugation does nothing. And so an example of this, simple example would be, for example, 0, 1, 1, 0, because say I take the Hermitian conjugate of that, so this is equal to taking the transpose and then the conjugation, or the other way around if you like. So this is equal to, say I do the transpose of this, so I flip the rows and the columns. So actually this happens to be a symmetric matrix, so even after the transpose, so this is doing the transpose part, right? Now I need to take the complex conjugate of this, and everything is a real number, So it's just equal to the same matrix. Okay. Maybe a slightly more interesting example is another matrix that looks like this. So say I've got some i's in here. Okay. So say to take this matrix, 0 minus I, and 0. Now I take the transpose of this. Now I'm going to get a different matrix this time. Okay. And then I take the complex conjugate. Now, even though I ended up with the different matrix here, taking the complex conjugate, I'm actually going to end up with the same matrix as I started with. So this is an example. Well, both of these ones are. Put a star here. So this one was doing the transpose. So I should put the DAG here. So this is these are examples of Hermitian matrices, and why is this important? Because actually quantum mechanics, all the observables, so all the things that you can actually measure, it turns out are related to matrices which are Hermitian. So you'll have to just take this as a kind of axiom of quantum mechanics. It's just sort of like, why should it be Hermitian? Well, yeah, I mean it's a little bit complicated to explain. I think I can't do a very good job for this kind of introductory level, but it basically has to do with the properties of the Hermitian operators. And one of the important properties of a Hermitian matrix is that all its basically you can only give real numbers as its sort of output, if you like. We'll talk about eigenvalues in a moment, but these basically it can only give real numbers as its kind of output. So if you try and find what the kind of the average value or some um, uh, value that you can sort of extract from these observables, then it really needs to be something real, because everything that you observe in the real world is got to do with real numbers, not complex numbers. So this is one reason why Hermitian operators turn out to be exactly the right type of formulation for something to be an observable in quantum mechanics. But okay, I think for the level that we're doing here, I think just take it as, okay, well, there's some mathematical properties which this satisfies that matches up exactly with what you need for an observable. Okay. We'll talk about more about observables later. Okay. So let's talk a little bit more about some other types of um, matrices. So there are some other special matrices. So the first one is, well, the first one that we'll look at is the identity matrix. So the identity matrix is nothing but the matrix where you've just got ones on the diagonal and zeros everywhere else. So this is called the identity matrix because this is a special matrix that has the special property that if you multiply this matrix I with any vector, you can take any vector, then you'll get basically the same vector. And another way of writing this vector is in this form. So we talked a little bit about the outer products before. So if you remember, these things basically give you like some of these matrix elements with 1 somewhere and 0 everywhere else. So for example, in this case, the actual matrix form of this would be like 1 in the top corner, zeros everywhere else. So 0, 0, 0, 0, dot, everywhere else is 0, right? So this is basically the matrix with the 1 just in this corner here. This would be the matrix corresponding to the 1 in the second spot. So the first one is 0, everywhere else is first one is 0, the second diagonal will be 1, but everywhere else will be 0. So these will be all 0, and dot, 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 right? Okay, so obviously if you add all these guys together, then you'll end up with this matrix. So this is another way of writing the identity matrix. Now this is actually, this identity, or well, this way of writing the identity matrix is actually probably one of the most used tricks that you use in quantum mechanics. It's like the trick that everybody uses. So this is why I sort of wanted to introduce it here. It looks really kind of obvious, but actually it's a really very useful trick that you'll use over and over again when you do quantum mechanical calculations. Okay, so that's okay for now, just a type of matrix. Now we can also talk about adding and multiplying operators. So before we were talking about adding and multiplying vectors, but we can also add and multiply operators together. So for example, if you add two operators, then you can, because these are sort of linear operators, you can actually add the operator first and then multiply that with the vector in question, or you can actually operate on the vectors individually, then add the vectors together individually. Right? So S times alpha gives some new vector, T times alpha gives some other vector, then you just add those two vectors together. So that's kind of addition of operators, but you can work out these things in the way that is most convenient for the calculation that you're doing. Multiplication of vectors. So this is where things get a little bit interesting. So I've said that operators are a little bit like some kind of machines that you stick in a vector and then it spits out a new vector, right? So this is an example here. So we've stuck in a vector alpha into this operator t. T acts on alpha, now makes a new vector alpha prime. We'll visualize it somehow like this. So here's our original vector. This operator t has taken it from this original vector to the final vector here, alpha prime. But we can actually then stick that into another machine, right, S, and we'll get yet another vector, right, alpha prime prime. So how we'd write that, of course, so if we just write this part of the equation, then of course it's like S acting on alpha prime, and then this gives alpha prime prime, but we've got an equation for alpha prime, so in other words, the double application of the operator, so we started with alpha, then we applied T, applied S, this is how you would write this in this kind of notation. So this final vector, so if we just view this whole thing here as kind of like one machine, so we don't worry about what's happening on the inside of this machine. So we just view this whole thing as this machine. Then we can view this operator of T and the S just as sort of one machine, and that would be basically this part of it. So if we could call this another letter, so ST, say we call it W, then this operator W, you would say that this operator W is actually equal to operator S times operator T. So notice that the order of these things is actually kind of the opposite of the order that we're writing it here. And this is something that you'll have to always keep in mind of, where there's a little bit of different way of writing it when you write it as an equation as opposed to sort of this kind of flow chart here. We'll actually encounter this kind of thing with quantum circuits. So when you write a quantum circuit, you actually write it sort of in this way, where a state sort of goes from left to right, where if you actually write it in terms of mathematics, actually everything is reversed. So it's a common mistake that people make. So keep a lookout for that. In the matrix notation looks a lot like the operator notation. So essentially what we're doing is we're taking this initial vector, that this was the components of alpha, then we're multiplying it by the operator t, where you do the matrix multiplication and we get a new vector, and then the output of that is applied to this operator s, which is also another matrix multiplication. So that basically the application of t and then s is basically written as just one giant matrix equation like this. And you can imagine that you can repeat this for many, many operators. So, we'll have like a chain of operators applying on the output of one sort of successively. Right. Okay. So, and this brings me to the so-called commutator. So what's kind of interesting about these operators is that, so you really have to keep in mind that these things are kind of not the same as these algebraic quantities, and this is why sometimes people like to always make it clear that these things are operators and not like just regular algebraic variables. So normally, if you've got some algebraic variables like, let's call it x and y, we all know that xy is equal to yx, right? So, 3 times 5 is the same as 5 times 3. But when you're doing operators, you have to be careful because that is actually not true, right? So I should really write not true. So operators and matrix basically do not obey that. So st is not equal to ts always. Sometimes they can be, but not always. And so this quantity called the commutator kind of gives you an idea of how much the operators don't obey this property that it's the same no matter what order you do the operation. So, for example, let's say you have two operators, s and t. So again, I've got the hats here, but so if you really wanted to make sure that it was clear that it was operators, you should put hats on everything. So this st, so this should be a comma, by the way. So it's not very clear on the slide, but it should be a comma. So s comma t in these square brackets, what that actually means is st minus ts. And of course, if st was equal to ts, then this would be equal to 0. But for operators, often it's not, and this basically tells you sort of how different it is to the to the regular case that we're very used to, where things are the same no matter what order, right? So basically, you would say that something like this commutes. So if xy equals yx or ts is equal to st, you would say that the s and t, or x and y, they commute. So the order does not matter. But if they do not commute, then, well, you just say they do not commute. And you can evaluate this thing called the commutator, which kind of tells you kind of how much it doesn't commute, roughly speaking. Okay, so let's just do a couple of questions to just get used to all this notation. So for example, say we have these matrices x, y, z. So actually, this is I brought up some of these examples here. So if you take the Hermitian conjugate of x, then this is actually just equal to x. So this is actually equal to, I did this a couple of slides ago, so I won't go through it again. And likewise, I showed that actually y dagger or y Hermitian conjugate is also equal to y. And it's actually pretty easy to show that z Hermitian conjugate is also equal to z, because let's just work it out. So z Hermitian conjugate, so this is equal to, so z, so let's do the transpose first. So this is equal to basically z transpose and then taking the star of that. So let's take the transpose of this one. So if you exchange the rows and the columns, then the 0 goes to 0, and then the 1s, these ones are in the same spot. So actually this is the same matrix. So the transpose does not actually affect the matrix. And then we've got to take the complex conjugate of this thing. Now everything's a real number, so we don't have to change anything, and we actually get exactly the same matrix. So this is equal to just z. Okay, so we can actually see that these three matrices x, y, z are all Hermitian matrices. So actually, I brought up these examples not just purely out of thin air. These are actually very common matrices that people use in quantum mechanics, and so at this level, you just have to, they might as well just be some random matrices that I picked out of the air, but we'll actually come back to these matrices quite often. Okay, second question here is to evaluate x commutator with y. So the definition of this thing is x times y minus y times x. Okay, so let's first work out what xy is. So xy is, okay, so let's write out the matrix. So it's 0, 1, 1, 0, and this is 0 with minus I and I and 0 there. Okay, so now we just have to do this matrix multiplication. So we take this column here, and then we multiply it by this row. So just do that in my head there. So this gives actually plus I. For this element, we take this column and then multiply it by this row. And so it's like minus I times 0 plus 0 times 1. So that's actually 0. Now, for this spot here, we take this column and multiply by this row. That's 0 times 1 plus I times 0. So that's again 0. And finally, for this spot here, I take this column, multiply by this row, so it's minus I times 1 plus 0, so it's minus I. Okay, now let's do yx. Okay, so yx, we've got to reverse the order of these things. So this is minus I, this is plus I, this is 0. This is 0, 1, 1, 0. Okay. And again, we take this column, multiply by this row, we're going to get minus I. So we can already see that this thing is actually not going to give the same matrix. So actually, we can already see that this thing is not going to commute. But let's work out the rest of the elements. So this column and this row, so that's going to be 0. This column and this row is also going to be 0. This column, this row, that's going to be plus I. Okay, and then we've got to subtract those two things. So the commutator, so that was supposed to be a comma there. Okay, is going to be this one minus this one. So I minus minus I is 2I. 0 minus 0 is 0. 0 minus 0 is 0. minus I is minus 2I. And in principle, that's the answer. But actually, there's a neat way of writing this, which is actually, if you notice that this thing is just a multiple of z, we can actually equally write this as 2iz. Okay. And this is actually also another property of these matrices that we'll encounter later. Okay. Turns out that if you do the commutator of these other matrices, so for example, you did commutator of y and z, so y comma z, then you actually get 2ix, and you also, if you did commutator of z comma x, then you get 2iy. So you can check that out for yourself, and it's actually good practice for working out these things. Okay, so let's move on to the last bits of these matrices. So as we've been discussing, so normally when an operator acts on a vector, it will actually change the vector here, right? So applying t onto alpha will normally give you a different vector, right? But there are some special vectors which turn out to be kind of unchanged when the operator kind of acts on it. So um, these are, again, it's kind of like a symmetry of the operator, if you like. So these are like special vectors where it's immune to the effects of the operator. And so these are called the so-called eigenvectors, and these actually have a very special kind of, these are very useful in terms of kind of knowing the properties of the matrix, and actually they'll also be very important in terms of quantum mechanics. We'll probably not actually go into a lot of detail in this course, but so for example, if you are trying to find energy levels of an atom or something like this, it turns out that you really need to find these kind of eigenvalues and eigenvectors. So, but basically, I'm just introducing it to you now. And for example, here's a particular eigenvector. So these are called eigenvectors, and uh, these are unchanged up to some kind of constant. So it's basically gives the same vector, but it might be like proportional to it. So it's the same vector, but maybe it's like elongated, or maybe it's shrunk or something like this. So this factor, the scalar factor that it elongates the vector or shrinks it, is this eigenvalue. And an operator might have more than one eigenvalue. In fact, for a Hermitian operator, it will have as many eigenvalues as the dimension. So if it's like a 2 by 2 matrix, then there will be two eigenvectors and eigenvalues if it's a Hermitian operator. Okay, so those eigenvectors, and another final thing which is actually quite important conceptually is you can always actually represent vectors in more than one way, and this is basically through a basis transformation. Um, so take this example here. So here's our vector alpha, and remember that we could write that vector alpha in terms of these components, which are really defined just, according to whatever axes that you happen to choose, right? So this, if you happen to choose these axes, like this red one here, then you would get certain coordinates like A1 and A2, which are like going to be, for example, the projection of the this vector on this axis here. So for example, A1 would be like this length here from the origin to this projection here, A2 would be the projection of the vector along this axis. But there's no actual reason why we have to really choose this set of axes, right? So just to take a kind of an example, if somebody viewed a picture of, say, the space shuttle or something, um, and you were viewing the space shuttle from, say, two locations, then, depending on where you were, the space shuttle could look upside down or the right way up, or some other orientation. It's really dependent upon where which direction you are looking at it. So obviously the space shuttle is still the space shuttle. It doesn't change the fact that it's a space shuttle just because somebody else is looking at it, upside down or some other way. Um, uh, Basically, the way that you are looking at it gives you your sort of coordinates. So, for example, the red one might be you, but then the green one might be just somebody else who's just looking at the same thing from a slightly different angle, right? So the way that they view it will be a bit different to the way that you view it. And so, as I think I was explaining in some of the earlier slides, the coordinates that the other person, green guy here, would get would be just different to what you get. But it doesn't mean that it's a different vector. It just means you're just looking at it from a slightly different angle. So how do we, for example, get this one set of coordinates to the other? And this is actually where you can actually use these kind of operators. And so, for example, let's say I wanted to work out what your coordinates, or kind of what your axes are based on what my axes are, right? So there's basically a kind of a rule that changes my axes into your axes, right? So the red ones into the green ones. And the operator that does this is basically uh, is called a unitary operator, and it's you can say that it's more or less defined by how this bases or the coordinates actually change from your frame into some other person's frame. So this operator kind of transforms the vector as viewed by you into the vector as viewed by your friend, who's the guy with the green coordinates. And for reasons which I again will not really go into it, unitary operators, which tells you how to do this kind of transformation, have the property that the inverse of the operator, which is like the thing that undoes the operation, right? So the inverse of any operator is always defined as the thing that, so if you apply the inverse to it, to the operator itself, then it basically just gives the identity operator, which is the thing that basically does nothing, right? So, or another way to put it is that, say I've taken a vector, I've applied some operator on it, in this case this unitary operator, and say I want to get back my original operator. Like, how do I undo the operator? Then basically what I do is I apply the inverse of that operator, and then that will always give me back the original vector. That's the inverse is defined as the thing that just undoes the operation. So in this case, in this example, it would be the operator. It's like the thing that rotates the state from red to the green, and then the inverse would be the thing that rotates back from the green to the red. Okay, so that's the inverse, but the unitary operator has the property that it is the inverse is actually just this kind of Hermitian conjugate, so it didn't come out very well, but this should be not a plus, but like that dagger, the Hermitian conjugate meaning the transpose Hermitian conjugate. So there are certain types of operations like this, and it will turn out that actually these unitary operators are exactly what happens in a sort of a quantum mechanical evolution. In fact, like the Schrödinger equation that we briefly talked about a few weeks ago, I didn't know details, but that actually turns out to be one of these types of operations. Okay. So I think that's all I want to say about that for now. So now let's just finally go through this question here. So first question says, verify that this vector is an eigenvector of x. So to show that this is an eigenvector, let me move myself out of the way a little bit here. So to show that this is an eigenvector, all we have to do is just basically multiply this x by this lambda here, and because this x is, so we just do this matrix multiplication, 0, 1, 1, 0, and okay, so there's some constant here, over root 2, 1, and then minus 1. Okay, so now I've got that back. Let me move myself back. Okay, now we just have to do this matrix multiplication. So any time we've got this constant, we can just pull it out the front. It doesn't affect anything. And then we just go through and do the matrix multiplication. So again, we've got this column, and then we multiply by this row. So it's 1 times 0 plus 1 times minus 1. That's minus 1. We multiply this column by this row, so that's 1 times 1 plus 0 times minus 1, so that's 1. And this thing is actually equal to minus of 1 over square root of 2, 1 minus 1. So that's actually just equal to minus of the original vector that I just wrote down. So we would say, yes, it's an eigenvector of x because we've got the same vector up to some number, and the eigenvalue is actually equal to minus 1. So I would say the eigenvalue lambda 1 is equal to minus 1. Okay, second question, what are the eigenvalues of z? Okay, well, I haven't really told you how to do the eigenvalues or how to work out the eigenvalues systematically, but this is a particularly simple kind of matrix, so you can just about kind of see it just by looking at the matrix. So this is why I didn't really well, give you a systematic way to work it out, but so this matrix Z is equal to 1, 0, 0, minus 1. So we're just looking for a vector that, when you multiply this, would give you the same vector, right? So, well, if you multiplied any vector with any form, for example, like this, then what you would actually get, so let's just try this. So say I took any arbitrary vector AB, then what I get is A, and then 0, 8 times 1, 0 times B is A. Here it would be 0 minus 1 is B, so A minus B. Okay, so we've just about got the original vector, but it's actually clearly not an eigenstate for any values of A and B, because obviously AB is not the same as A and minus B. But you can just see from this example that, well, I should really say this is Z times some vector, okay, B. Yes, okay, so B is my vector here. Okay, so this is clearly not equal to v. Okay, or it's not anything proportional to v. But if I choose, for example, a is 1 and b equals 0, then it does work, because in that case this b is 0 anyway and doesn't really change anything. So this is one example where it is an eigenvector when I choose those numbers, and the eigenvalue in this case is equal to uh, is equal to 1, because in that case I get exactly the same vector. Another example is when a is equal to 0 and b is equal to 1. Okay, so in this case, the final vector that I'm going to get is actually 0 and then minus 1. Okay, so that uh, that value of b has flipped, but because this is 0, I can actually just write this as minus of 0, 1. And then in this case, if I take the eigenvalue is equal to minus 1, then it is an eigenvalue. So these two cases of a equals 1, b equals 0, and a equals 0, b equals 1, these are the eigenvalues and eigenvectors of Z. Okay, so that basically concludes this lecture on kind of a crash course in linear algebra. Now, I've probably gone through sort of more material than I really needed to do for this course, but that more or less should be all the things that you actually really need to know in terms of learning kind of quantum mechanics. So linear algebra, of course, has many more things that that you would need to know before you can say you really knew linear algebra. But in terms of learning quantum mechanics, those are the kind of things that you really need to know. And in fact, for the purpose of this course, you probably don't need to know even that much. But what you certainly do need to know are things like how do you multiply, matrices to vectors, how do you, calculate inner products, how do you, perform, certain operations like, again, matrix multiplication. So those kinds of basic operations are things that you'll need to do. Some of these other things like, the definitions of what it means for a matrix to be Hermitian and things like that. These are things that probably we won't really need to know so much in the course, but I think it's just good for you to know some of the sort of the background material. So please do go through the homework questions, and that will give you extra practice in manipulating these things, and that'll give you good foundation for the learning quantum mechanics. Okay, so I will leave it there for this lecture, and we will continue on next week with talking actually about real quantum mechanics. So this will be very exciting. So, okay, so we'll leave it there, and I will talk to you next week. Bye.